Today I'm going to discuss exercise, why we should all be doing it. Granted, we have the capacity to do so. Insulin typical, insulin atypical individuals, and basic digestion and absorption. All right. So say we begin by ingesting a donut. Okay. We ingest that donut, follows our GI tract, ends up in our small intestines, the chyme. Okay. We have our brush border enzymes, sucrase. It is going to break down the sucrose that we just ingested, which is donut. Okay, we're gonna break it down into fructose and glucose. All right, we have these cells lining the duodenum, or my bad, the small intestines. Okay, and these are going to secrete hormones, and these hormones are then going to travel to the pancreas. Okay, and they're gonna stimulate pancreatic cells to release insulin. Insulin is going to come up here and act on peripheral cells. All right, so that they could take up the incoming glucose. However, we have glucose and fructose heading down to the lower regions of the intestines and being absorbed, okay, in the intestinal epithelium, following into the nutrient-rich blood, now nutrient-rich, and then eventually being pumped via systemic circulation by the heart. After it's pumped, it is then going to be available systemically to be absorbed as depicted here. Okay, green, glucose, blue, insulin. Parallel lines, glucose transporter. So to begin, we have our skeletal muscle cells. So we have a bicep drawn here. I am not the artist in the family. So we have a skeletal muscle cell. We have the insulin receptor, insulin binding to the receptor. This is once again the ideal scenario. We have insulin binding, initiating a signaling pathway. I'm not going to discuss the exact pathway because it's too much details that we would get lost in. So to discuss this, we have AKT being stimulated. AKT is going to inhibit GSK3. This is going to be associated with increased glycogen formation, as well as down here, we see that GSK3 is associated with gluconeogenesis, so secreting glucose, which we will see subsequently, plaque formation, and tangle formation. These are observed in Alzheimer's disease. But to go back up here, we have GLUT4 transporters also being inserted into the membrane. This is important for actually taking up the glucose into the cells to be utilized. So it's going to then be utilized by being burned for energy to generate ATP so that our cells could function. And alternatively, we could just be storing it as glycogen. Finally, we have the mTOR pathway that is of interest. That is going to stimulate anabolic processes such as protein synthesis, so hypertrophy of your muscles, increasing the muscle size. A triglyceride synthesis. This is less so prominent in muscle tissue, more commonly seen in, say, adipocytes, so in your fatty stores. So that's for an insulin typical individual. But then we have an insulin atypical individual, so someone with insulin resistance. That term is commonly heard online, so I'm going to attempt to illustrate a bit what is meant by that. However, the mechanisms are not clearly delineated, but I will try. Okay, so this is for the insulin typical individual. Glucose is going to be taken up to be burned or stored. And then this is for this insulin atypical individual. Just a lot more glucose circulating, of course, because the patient is suffering from hyperglycemia now as a result of this impaired insulin. We aren't going to be taking up as much glucose because the cell is essentially well fed, so that's typically the root cause of this. And what I mean by that is typically these cells will take in fatty acids, okay, as an alternative fuel source. However, because they are already well fed, this is kind of unnecessary, clearly, by the excess glucose we have. Fatty acid oxidation is a process where the fatty acids are actually broken down into their components. And we see an increase in DAG, which is a component, it's an intermediate of the process. So we have our triglyceride broken into a diglyceride. DAGs, as these accumulate, they stimulate PKC delta, or epsilon. That is then going to go and inhibit the IRS1 PI3K. If this is inhibited, we see that we don't follow through with this pathway. Okay, and what that means is AKT, otherwise known as PKB, this pathway is impaired. So we see that the mTOR pathway, remember the anabolic process, these aren't going to occur. What that is going to result in is atrophy of our muscles, so the breakdown of our muscles, observed in sarcopenia. All right, so age-related frailty, loss of muscle mass, sarcopenia. We're going to observe that by downregulation of the mTOR pathway. We also see This translocation, okay, so a gradual increase in the glucose transporters being put into the membrane so that we can actually uptake the glucose, this is not happening. Hence, we see hyperglycemia, too much glucose in the plasma, because we aren't efficiently transporting these receptors into the membrane to take up that glucose, because our cells are essentially well fed. So we have GSK3. Usually it's being inhibited, however it's not going to be inhibited, so we will see increasing gluconeogenesis, so increasing in our glucose production. Why would our cell produce more glucose despite there being a lot of glucose in the blood? Well, that's because our cell doesn't know that there's a lot of glucose out there, because it relies on insulin to signal that. However, if this signaling is impaired, that is why we see this counterintuitive process occurring. Okay. We also see plaque accumulation and tangles of the axons in the cerebral tissue. All right. So this is why we see that insulin resistance is not only observed in diabetic patients, but is likewise going to be observed in any type of metabolic condition, including Alzheimer's disease. Okay. So that is why this is a concern. This is why GLP-1 agonists are in vogue for patients regardless of their blood glucose levels. All right, so we should always consider that. Okay. Finally, I'm going to discuss exercising tissues. So we have exercising tissues, okay, while fasted, cold, or exercising. This is why we see online that fasting, intermittent fasting, cold exposure, so like a cold plunge, and exercising, so daily exercise as much as we can tolerate, is immensely beneficial because it contributes to insulin sensitivity. So it amplifies the signal that insulin has on a given cell. What I mean by that is we produce AMPK and SIRT1 while we are fasted, cold, or exercising. And this is because when the ratio of AMP, so when we are essentially deprived of energy, our cells are deprived of energy, this is a natural process, we don't have enough ATP, okay, so we're going to downregulate processes associated with energy-rich conditions. All right, so we don't want to be producing more proteins, we don't want to be producing more triglycerides when we want to be burning triglycerides when we are energy poor, right? So we want to be creating energy, not storing energy. So it makes sense why we see that these two intermediates would downregulate anabolic processes, because we're going to kill ourselves essentially if we do that. Specifically though, we have AMPK stimulates AKT. Remember AKT earlier? AKT is involved in the traditional insulin signaling pathway, resulting in an upregulation of mTOR, translocation, so insertion of these glucose transporters into the membrane, as well as decreased plaque accumulation and narrow tangles via the inhibition of GSK3. We see that AMPK, it actually upregulates AKT. However, oddly enough, a further down intermediate, PGC1 alpha, actually inhibits the mTOR pathway. What does this mean? It's complex. We see that AMPK upregulates AKT, perhaps because, yes, we want to increase the uptake of glucose. That's fair. But then, as mentioned earlier, we wouldn't want to stimulate anabolic processes if we are fasted, exercising, or cold. We want to be using that energy efficiently. We want to be maintaining homeostasis in our cell, not building up our cells, okay? So that is why that is going to be inhibited by the downstream PGC1 alpha, okay? However, we have SIRT1, SIRT2 and 1. You might have heard about this online. But yeah, that also contributes to a PGC1 alpha upregulation. Okay, PGC1 alpha, very, very interesting molecule. PGC1 alpha contributes to mitochondrial biogenesis, quality control, and increased oxidative phosphorylation gene expression. What this means is that when we are fasting, exercising, or cold, okay, we want to increase oxidative capacity. All right, so our efficiency at burning fuel, essentially. So we are going to create more mitochondria. We are going to make sure that our pre-existing mitochondria aren't dysfunctioning. Okay, so we are going to degrade mitophagy, those mitochondria that are producing a lot of oxidative ROS, so reactive oxidative species. All right, that's implicated in, say, cancer. So that's a very good quality control mechanism there. And then increasing oxidative phosphorylation expression, and this is tied to the biogenesis, okay? Because if we are creating a lot of mitochondria, we want to create the proteins that are necessary to function within the mitochondria during the oxidative phosphorylation, the energy generating process. All right, so that all makes sense. So that's pretty much all I wanted to discuss in terms of the actual physiology. But To discuss the actual 3 types of exercise that are of interest, we have aerobic, resistance training, and HIIT training. HIIT training is going to be the best bang for your buck because it incorporates both aerobic as well as resistance training. So typically we observe that the AMPK process is involved in aerobic exercise, whereas the AKT pathway is predominant in resistance training. However, they are not mutually exclusive, and this is often a misconception because aerobic exercise is known to both benefit oxidative functionality but also to impair the plaque formation and the neurotangles from forming in the cerebral tissue, as well as we often see hypertrophy sometimes in people performing exclusively aerobic exercise. So that's a fine nuance. And resistance training being important for combating sarcopenia, so age-related frailty. So ensuring that you have adequate muscle mass to sustain the rest of your life, especially when you exceed a certain age where you are no longer able to put on such much muscle mass. So it's always prudent to begin exercising as soon as possible to stave off any sort of decline. So we have aerobic exercise, follows primarily this pathway. We have resistance training, which follows primarily this mTOR pathway, so hypertrophy. It is commonly conceptualized that aerobic exercise is primarily beneficial for oxidative functionality, combating Alzheimer's disease, whereas the mTOR pathway, the resistance training pathway, is for sarcopenia. It is always wise to do both, but HIIT training will always be the best bang for your buck because it incorporates both. Aerobic because it's focused on preventing cognitive decline, and resistance training because it'll significantly reduce your chances of falling, which we know to be cataclysmic for older populations.